Good afternoon. You've only got about another 40 minutes to go, so bear with us. I'm going to introduce the first part of this talk, and then Rob Bolin Francisco is going to take you through the latter part, really. This is actually a study that I kind of wanted to do for quite a long time. I was very lucky to work on Pearl River Tower, high-performance high-rise building in Guangzhou, as were several people in this room. And one thing that struck me after we'd finished the project was, given the climate, and the climate in Guangzhou is quite a challenging one from a humidity point of view, if nothing else, how would this building have to change if it were actually located in different parts of the world? Now, this is not going to be a presentation about Pearl River Tower, but what that really led on to was the number of, or the various numbers of cladding systems that one can kind of utilize on a building or choose to put on a building, coupled with all the myriad of building systems that one can use and the various climates around the world. How does the climate start to inform maybe some of the choices that you might make for both the building systems and the external envelope, and how those systems might interact with one another? So these are just some examples of high-performance facade systems that we're going to talk about later on in the paper. And there's various different ways of dealing with basically solar gains in a building and making sure that your building is performing at a very high level, you know, whether that's internally or externally ventilated. So how do you go about actually having some kind of ready reckoner in terms of how you go about approaching design of facade systems? You're particularly working in China. You know, you have to generate the concepts very early on, you know, and 8 days later you have to provide a rendering of something. And, you know, which is always a challenge for most architects, because we really don't know necessarily what the systems are. So what we decided to do in this study was to actually have a generic building, you know, I don't know, a typical 1.8 million square feet commercial office building, and place it in the different climatic zones across the world, and just see how we can test these with a number of approaches, both from an exterior wall point of view and also from mechanical systems that we might employ in the building. And I apologize for anybody from the Southern Hemisphere, you're not really represented here. What we've decided to do was actually to take, I think, the 12 different climate zones as defined by ASHRAE, and look at how this generic building might perform across the world, if you like, on these various different climates. I'm not going to go through them all, but you can say we've kind of listed, as ASHRAE defines them, in terms of what these areas are. Now, obviously, there are other spots in the world that have the same climatic conditions, and you know, if it was in South America, we would be picking one of these climate zones. So we tried to represent, because actually all these ASHRAE climate conditions are actually applicable to North America. Pretty much all of them exist in North America at some point, but given the nature of the conference and its kind of global reach, we decided to try to place this building in various cities across the globe. We also decided, and again, sort of rather arbitrarily, we took 7 different skin approaches to the building to see how they might perform. And we also, as I mentioned earlier, we decided on 3 systems to actually utilize to test with all of these various combinations. So what actually comes out of this is actually a pretty extensive, and given the time available and the time that we had to prepare the paper, it's a pretty broad brush kind of approach, but I think it's interesting just to show you some of the findings that we found. Other things that we looked at were kind of window to wall ratio. We also looked at orientation. So there's 3, within these 12 climate zones, 7 cladding systems, 3 building systems. We've also got 3 building orientations to kind of take account of. And the methodology that we use, this is a slightly weird slide, but I think it comes up twice. We looked at basically a square format building. So this is typically a 45 by 45 meter square building. It's a 2,300 square meter floor plate, 25,000 square feet of floor plate. So this is all things that we're all familiar with in terms of building high-rise buildings. And then we also looked at two other variants of that in terms of rectilinear buildings, one on a north-south axis and one on an east-west axis. And what you see here is actually the 7 different cladding systems and the 3 different approaches to the HVAC. We generated over 500 possible combinations, so there was a lot of number crunching, which fortunately I didn't have to do, but Rob did. And this starts to actually identify an important part of the methodology, because what we had to do, and what actually we did for Pearl River Tower, when you're measuring kind of building performance, you obviously have to have a base building. So what we did is we had an adjusted base building, because actually 90.1 is based on 40% glazing, and almost no high-rise building is 40% glazed. So we adjusted this to reflect a more typical high-rise building, commercial high-rise building. So we have 65% glazing, and we adjusted the performance of the glazing to match the characteristics of being ASHRAE compliant. We then went through a number of various skin options, and a lot of the early ones, IGU1 through to 3, are really just playing around with a double glazed IGU and with various low E coatings on it, so the level of transparency on the glazing is variable. We then went to a fritted option in this combination, and then we also went to a triple glazed option. Then on the 6th option of 7, we actually introduced some external solar shading. Now, I mean, obviously, depending on the height of your building and where it is in the world, you know, this may or may not be an option. But again, there's no climate specific, because the external shading option has actually been adjusted to the climate, so there's no particular performance. It depends on the climate that it's in. And the last option that we looked at in terms of facade type was a high-performing, double-skin, ventilated, internally ventilated cavity with a fully mechanized blind system in the cavity. So those are our 7 types. We've already identified our 12 climate zones, and we've got 3 building orientations, so I hope you're kind of keeping up with the maths at the moment. We then actually started to look at the various HVAC systems in connection with these. And we looked at a typical overhead VAV system. So that was one option. The second option we looked at was a floor-fed air distribution system, so to see how that might perform. And the third option was actually using chilled water to do the cooling rather than using an air system. So that pretty much sets the context or the broad scope of the problem we were trying to, well, not problem we were trying to solve. We were just trying to see what relationship some of these glazing systems integrated with its building systems in particular climates with a particular building orientation might throw up. So this is a trickier bit, so I'm going to hand over to Rob. Do you want the mic, or are you going to use that? That goes forward. And that's a little pointer.
All right, so I get the unenviable task of trying to make sense of this big sort of chaotic mess that we've got in terms of all of this analysis work. So this is just a summary slide. You can actually see this in the proceedings. A little bit more information, a lot more description of what what the overall results were amongst the various different configurations that we had. So setting initially sort of the context of how we referred to the energy, there's a couple of different ways that you can refer to the energy for the building. There's a site energy, very specific to your building envelope, just what you're using at the building versus source when you take it back, obviously, all the way to the energy plant, and you account for all the distribution losses that you have. And so, you know, very simplistically, when you look at site energy, it's all the loads inside the building for heating, lighting, HVAC, elevators, what have you, divided by the gross building area site energy use intensity, a very simplistic way, and a lot of people actually do refer to energy use intensity in this way. We have a tendency to prefer to actually look a little bit more beyond just the footprint of the building and see how that is being impacted by the type of energy that you're using, or the source of the fuel that you're using to generate the energy. So when you look at source energy, you are actually taking the transmission, delivery, and production losses into account, then dividing it by the gross building area to give you the source energy. So contextually, we're talking, when you see numbers here, about source energy, what is actually required to generate the amount of energy that you're using in the building. Very quickly to the results. So the first step that we took was to really sort of look at that massing and orientation that Russell referred to. So we've got the three different massing orientations, and an east-west orientation, a north-south orientation, and then a square orientation that gives you essentially the same amount of area on each facade. And see if this is telling us anything that we don't really anticipate. On topic, I know that some of you are in the southern hemisphere. I'm going to talk very specifically about obviously northern hemisphere here, because those are the climate zones that we have. But not surprisingly, it's pretty intuitive, the results, the east-west orientation with long north and south sides in terms of energy performance on the baseline ASHRAE VAV system. That east-west orientation in all climate zones is better. So we took that particular east-west orientation, and then we ran it through sort of the first characteristic. ASHRAE Standard 90 has a baseline overhead VAV with reheat as its baseline system that it describes. So that's where we sort of started, and then we evaluated we evaluated various different envelope systems according to that particular baseline HVAC system. So in this particular case, we're looking at the overhead VAV, the underfloor air distribution, and then it's actually an active chilled beam system that we've got for that third case to see what kind of trending and what kind of sensitivity analysis that we were actually getting. And not surprisingly, really, what we found was that the underfloor air distribution system, by and large, was giving us the best energy performance throughout the bulk of the climate zones. There's a couple of outliers here in Mumbai and in Riyadh and Mumbai, where it's hot and humid, and you have very little, if any, heating season. What we were finding is that the chill beam is actually performing roughly equivalent or slightly better in the case of Riyadh in terms of energy performance. And then when you get to the heating-dominated climate, over here, Moscow, Quebec, what we're finding is that because there's significantly less cooling that's happening there, the idea of actually using chill water as your primary means of cooling rather than air, where you can take advantage of outside air economizer for free cooling, meant that the chill beam was actually performing worse. But in all cases, the underfloor air, with the exception of these couple of outliers, on that baseline double glazing system was the best performer. So then we went to the other end of the spectrum, looking at the baseline. What happens if we go to the ventilated facade? Would we see something different? And the trending essentially was the same. However, the numbers came down. We were seeing roughly 5 to 7% improvement in terms of overall energy, which actually, when you put that in the context of the impact of the building envelope on the overall energy in a building, is pretty significant. So again, sort of setting context. Most buildings, super tall is a little bit different, but most buildings, roughly a third of the energy in the buildings for lighting, a third of the energy is for power, a third of the energy is for HVAC. Building envelope, as a climate moderator, really doesn't have an impact on 1/3 of that energy. The equipment power inside, not impacted by the building envelope. The lighting is, depending upon what you do in terms of daylight incorporation, there's a little bit that actually happens. There's some improvements that can be made, but it's mostly on the HVAC. So most of the energy savings from the envelope affects only a third of the pie. Okay, so if you're reducing the overall element 5 to 10%, then the savings actually due to the envelope for the component that it impacts is pretty significant. It's roughly 15 to 20%. So it's a big piece, even though contextually overall it sounds like a smaller piece. So this next sequence of slides, and I'd encourage everybody to dive a little bit deeper into the proceedings so that you get a little bit more time to sort of review this, is that we went through each of the different individual systems and then evaluated, or at least charted, the performance of each of the individual glazing components that we evaluated to see again if we could find any specific trends. And most of the trends, not surprisingly, if you do a little bit better in terms of the glazing performance with regard to solar heat gain coefficient, yeah, it's sort of dropping the energy a bit. What we were a little bit surprised about, however, is that there are a couple of sort of outliers with regard to Mumbai and Riyadh, where the climate, again, there's very little heating, if any heating that's going on, but they're very humid climates. And so and this is probably a little bit more explicit in the underfloor air slide, but because you have to subcool and then reheat the underfloor air, there's a sort of energy penalty there. But generally speaking, what we found is that the trends were more or less consistent for each of the different system types as you sort of move from an improved glazing performance, U factor, and solar heat gain coefficient. So it wasn't really terribly surprising. Again, what this also is going to show is that as we move from, I'll back up here, the VAV with overhead, and then into the underfloor air system, you saw obviously the energy numbers as a bulk, all of them sort of drop by comparison. And then when we go to the ventilated shield beams, they sort of tick back up a little bit. So the trending is consistent, and it's consistent for each of the different climate zones by and large. There's a few outliers that are pretty specific when you get into the extremes. So a few of the sort of takeaways that we get from this very sort of broad brush study. The required solar heat gain coefficient in hot climates is significantly low at 0.17. So an improved envelope would need to utilize heavily tinted or fritted glass. The triple glazing performs well in both hot and cold climates, but its improvement is much more significant in cold climates such as Moscow, fairly intuitive. The ventilated cavity walls perform the best given their improved U factor, solar heat gain coefficient, and opportunity for incorporating active shading systems. So when they were modeled to deploy blinds based upon what the sun was doing around the building. The use of the external shading consistently improves the envelope energy performance in general, but may not be practical to incorporate. We know this. So that horizontal shade that we had modeled was slightly better improvement. It wasn't significantly better improvement, but it was better in general for each of the climate zones. The underfloor air distribution system generally performs the best among the systems modeled, especially in modeling in cooler climates with reasonable wet bulb temperatures. And the combination of the ventilated cavity wall envelope with an underfloor air distribution system was generally the best performer regardless of the specific climate. So that seemed to be a very strong tie together that, again, somewhat intuitive. Now, a couple of sort of notes here on this analysis. Very specifically, look just at energy. Now, we know that when we're selecting the systems inside the building, we're also selecting the buildings inside the building to make sure that we're providing thermal comfort, indoor air quality, ventilation effectiveness, that sort of thing. So these are things that are not necessarily part of this study. These are things that we see as sort of a next step in terms of perhaps doing a deeper dive on this particular component to see whether or not that becomes a more significant trending opportunity. But from my perspective, what we saw here in terms of this broad brush study was fairly intuitive, kind of what we expected, with a few sort of outliers that, you know, a super high-performing envelope, like an internally ventilated cavity wall that's got active solar shading devices combined with a high-performance underfloor air distribution system, is really a preferred solution if you're able to marry those to the envelope system with the HVAC system. And that's it.